This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Hello, this is Adam Gordon-Bell for Software Engineering Radio. Today, I'm speaking with Stephen Wolfram. Stephen is a scientist, creator of Wolfram Language, Mathematica, also Wolfram Alpha, and the CEO of Wolfram Research. Stephen, welcome to Software Engineering Radio.
Thank you.
So you have this new book, Adventures of a Computational Explorer. But I thought it might be fun to start talking about Mathematica and some of the programming language work you've done. And maybe we'll get to some of the interesting book stuff towards the latter part.
Sure. The book is kind of my strange adventures that come from taking the computational paradigm seriously, so to speak.
I want to start maybe with some basics. What is Mathematica? What is Wolfram language? Like, where did they come from? What's the goal?
Where did they come from? When I was a kid, I was interested in physics and discovered that you could learn a lot of stuff about something like physics just by reading books. Now with the internet, but back then it was just books. And really wanted to do physics research and really didn't like doing the kind of mechanical mathematical calculations that you needed to do for physics research. So I kind of very early on got this idea. This was back in probably 1973 or something. Got this when I was like 13 years old. So I'm old now. And kind of got this idea that this was something that was boring and mechanical for humans. Surely one could just automate it and get computers to do it. So that got me kind of on the path of how can I automate things like mathematical computation and make them be doable by computer. And my first language, which is called SMP, Symbolic Manipulation Program, sort of one of its important features was that it was dealing with everything symbolically. So, an X, you can just say, type in X, and it comes back as X. It's perfectly happy to just deal with X as a symbolic thing. It doesn't say, oh, no, error, needs to have a value, and so on. And in SMP, I kind of, I would say I tried out some fairly radical ideas about thinking about programs as being primarily transformations on symbolic expressions. That sort of everything, like when you evaluate a function, what are you doing? You're really transforming f of x to whatever the value of the function is, and thinking about that as transforming a symbolic expression from the input to the output, so to speak, and that was the primary operation of the language.
So that sounds a lot like Lisp, I guess, to me.
A little bit. I mean, except that one of the things that, so certainly Lisp, I would say that in the early days, Lisp and APL were my two kind of most, languages that were kind of most relevant sort of design, inspirations, along with C, I guess. I mean, SMP was kind of, I started using C as the implementation language for SMP back in 1979, before C was really so much of a thing. And the person who persuaded me to do that was a student who was sort of working with me at the time named Rob Pike, who went on to build Go and has always been a minimalist. And at that time was like, C is the language of the future. There's a little micro footnote to history for you. But the difference is that in kind of the symbolic languages I deal with, you kind of take seriously the fact that you can just have symbolic stuff lying around, and that there is an automatic infinite evaluation that occurs whenever it can. It's a little different from kind of the way one thinks about evaluation in something like Lisp.
Oh, what does that mean? Like, I don't follow. What does it mean for evaluation to be infinite?
We're, by the way, still at the very early stages of the story here, so there's much more to say. So, I mean, what it means is if you have defined a series of transformation rules that define, one's used to doing this with functions, one's less used to doing it with variables, but those really aren't any different in Wolfram language and in the kind of symbolic framework that we have. But basically, the idea is that if you give some input, then what will happen is transformation rules will occur until you reach a fixed point, basically. And that's the result of your computation. So, whenever you type in, if you go ask Siri some question that goes to Wolfram Alpha, the natural language will be turned into Wolfram language symbolic language. And then what will happen sort of under the hood at some low level is there'll be a whole giant series of transformation rules applied And in the end, there will be some fixed point reached, and that's the result. And then, it will say back to you whatever it says the answer is, so to speak. I mean, that's the very low level version of what's happening now. The user experience. I have to say, I don't think I've talked about infinite evaluation in decades because it seems natural to people, and so nobody ever says, "Oh, that's." But since you brought up Lisp, I remember when SMP and then later Mathematica and Wolfram Language were young, people would sometimes say, "It's impossible. It can't work. You can't build a system that has infinite evaluation." And they're thinking about things like if you type x equals x plus 1, what does it do?
Oh, I see. I see now. Yeah.
And it turns out, it runs into some limit, and turns out nobody cares. It turns out one of the features of language design that's kind of interesting to me is always these things where, one of my meta claims about language design, the only language design in which nothing weird could ever happen is a language which does absolutely nothing. And so the question is, the places where weird things happen, are they things that people actually run into in practice or not? And turns out that I can say after, 40 years or something, that's one where it turns out nobody cares. It turns out people don't run into it in writing real programs. And even though from a theoretical point of view, the something where you could say, oh my gosh, there's this corner, you could run into it, it would be terrible type thing, and it's undefined what happens, that's not sort of the important thing in practice. But this is really a footnote to a footnote about the relationship to Lisp and its evaluation strategy. As I said, it's probably one of the least important features of kind of the whole tower of stuff that I've tried to build.
Well, so I was just asking you because, like, as a software engineer, I try to look at languages and figure out, what family it fits in, like where that helps me have a context for, how you solve problems in this world.
Yeah, I think if we were talking about it, Wolfram language as like human languages, it would be an isolate. I would say it has ideas from many languages, and many languages now have taken ideas from it, actually. But its goals are very different from the traditional programming languages. I mean, you can use it as a quotes programming language, but that is kind of to get only a small part of the value that it has to offer, so to speak. And I think, the big story has to do with being able to express all sorts of things computationally. And for Mathematica, I kind of cleaned up and extended my kind of ideas about computational languages. And in the end, we kind of have rebranded the language and the stuff that Mathematica does as Wolfram language, because I got so fed up with people just saying, I don't do math, I don't need to use your stuff.
I think that helps me understand. You created this to help with math, but it became a much wider thing. And so you've rebranded it from Mathematica to Wolfram language. So who's the primary user of it now? Is it still within the science math domain, or?
Well, I mean, it's been around. So since it's been around for 31 years, it's got lots of people who've used it for a long, long time. So there are site licenses for our technology at basically all the major universities in the US and many outside the US as well. It gets used by, R&D folk. It's always really neat to me that kind of the world's highest end R&D folk turn out, unbeknownst to me, when I run into them, they're like, oh yeah, I've used your products for 20 years type thing, which is really neat. I would say that it's widely used in the R&D sphere, particularly kind of the high end of R&D, widely used in higher education. As we move forward, it gets progressively used in sort of more general production and enterprise settings. And that's been kind of the story of the last few years, is setting up Wolfram language so that it is really deployable in the cloud, in embedded settings, as in different kinds of containerized mechanisms and so on, so that it can really be integrated into sort of large-scale production systems, and it is integrated now into a whole bunch of large-scale production systems in sort of the Fortune 50 companies and elsewhere. So the typical use of Wolfram language, we invented these things called notebooks that have become quite popular finally in recent years, but we invented them in exactly the form basically that they exist today and back in 1988 when the first version of Mathematica came out. And it's actually one of the things I really like is that I can take a Mathematica version 1 notebook and I can run it, in version 12 of Wolfram language or in the cloud, and it actually works, which is very encouraging to me and important to me because actually I'm, for example, just working on a big basic science project right now where I did a little bit on it in the mid 1990s, a little bit on it in around 2004, and now I'm sort of restarting this. And by golly, the notebooks that I created at those times still run.
Oh, wow.
And so, Wolfram language has been very consistent. It's one of the very few examples of a language where code that people wrote in version 1 back in 1988 still runs today. And it's a heavy burden as a language designer because it's like you don't get to make too many mistakes if you want that to happen far into the future, so to speak.
I'd like to talk at some point about the language design aspects of it, but I don't want to skip over notebooks because super interesting area that you were obviously a pioneer in. So could you describe what this notebook approach to computing is? Maybe explain it to people who aren't familiar?
Yeah. It's very simple. It's just kind of how you interact with a computation. So the basic thing you're doing is you're saying to the when you're computing, you're basically saying there's input, there's output. You say, what's 2 plus 2? You press Shift Enter, it comes back as 4. But that's part of a document, and the notebook document can have text and section headings, and we made it have hierarchical structure back from the very beginning, and it's organized in this collection of cells, and so each piece of like input and output is a cell, and then there could be like section heading cells, and those will automatically group things underneath them. So you like double click the section heading cell and it will close itself up in an outline.
So what you're describing, it's like Wolfram language is not a text files that get run by an interpreter. Wolfram language is like a something like an interactive Word doc or Excel document where you can execute code in it and have visual elements. Is that?
Sure. But yes, for example, when I use Wolfram language, like this morning, I was writing a bunch of code and, it's in notebooks. In fact, some of the particular notebooks I was writing will get ingested into our function repository so that when people use them, they will just be they'll just be functions that they define that they'll just use as functions. And they could always go look at the source notebook if they wanted to. But as far as they're concerned, it doesn't really make any difference that code was written in a notebook as opposed to written in a text file.
And I'm sure a lot of people listening are thinking of Jupyter notebooks. And is that inspired by your work?
Well, according to Fernando Perez, he says he took Mathematica notebooks and made a version of them for Python. Yeah. I think they don't have a lot of the features that our notebooks have, but yes, they came from our stuff and in great detail, actually. Even the detailed prompts are the same and so on. But I'm not an expert on them because I don't use them, although you can call Wolfram language from inside Jupyter these days. You can call our Wolfram engine system that way if you want to. In fact, you can even call the free Wolfram engine for developers from inside Jupyter.
Oh, very cool. So it's very interesting, this approach to computing. What advantages does this notebook format give you when you're coding?
Well, sort of everything happens instantly. I've got, I press Shift Enter and then I run the code and it's right there. And I've got my sort of test examples right there, so to speak. And the other thing that is a huge advantage in Wolfram language, which is probably not so obvious unless you've experienced it, is that in a symbolic language, every piece of code runs on its own. Everything stands on its own. So you can always take any piece of code out of any other piece of code and it is runnable separately. You don't need to build a harness for it. It is just a runnable, executable thing. I would say what tends to happen is that people write sort of small scale algorithmic things directly in notebooks. By the time one's working on large scale, multi-user, sort of source controlled software projects, people tend to go to using some IDE. We have one called Wolfram Workbench that's based on Eclipse, but there are a bunch of other IDEs that work with Wolfram language. And people will then, by the time it's huge blobs of code, it tends to be using more traditional IDE type technology. But the thing that for doing exploratory work, notebooks are the best. I mean, and that's what, for doing data science, for doing R&D. I mean, for data science, the key thing is that what you use to develop things is what you use to deliver your final report. So I'm very big on this idea of computational essays, which are kind of ways to, it's sort of a new form of explaining things, where you have a little piece of code, a little piece of text, and then you'll have a piece of computational language and its output. And the idea is that when you're explaining what's going on, you're mixing kind of the explanation with natural language, with human language, and the explanation from computational language. Now, again, that sort of depends a little bit on our technology stack, but the end result, I mean, that's, it's kind of what I've been doing for, 30-something years, including I've done quite a lot of basic science over that period of time. And that's kind of how I've done that, is everything is kind of set up in notebooks and in these computational essays where I'm kind of explaining what's happening to myself or to other people. But the full code is there and everything is runnable. And actually something that we now have available is notebook publishing. So you can take one of these notebooks that you created either on the desktop or in the cloud, and you can publish it. And we just provide a server that allows you to freely publish notebooks, so that people can then, anybody in the world can go to a published notebook. It just comes up as a web page and can interact with it. So they can, resize the graphics, they can rotate the 3D images, they can move the sliders and the manipulates and so on, and they can sort of open and close cell groups and things like that. And then there's a button that says make your own copy. And if you make your own copy, then you get an editable version of the notebook that you can then go and start modifying the code, modifying whatever you want to modify, and redo the computations. So I think it's a really, really powerful way of sort of integrating both the doing of things like data science and the deployment and the kind of presenting of results from things like data science.
I was looking at some examples of these computational essays to try to wrap my head around it. It's a pretty interesting thing. So it strikes me as it's something like a way to do scientific papers, but even maybe more casually. So I found one that was like talking about the Civil War or something, and it had like paragraphs talking about where the various battles are, and then it had some Wolfram code that was like, it basically like pulled out the locations of the battles and like threw them on a map. So it was kind of an interactive essay kind of explaining it. But what are some other interesting examples of kind of combining, prose and code?
Oh gosh, I mean, there are tons of them. There's a whole notebook archive that we're in the process of getting up that has examples. The really weird thing about it is it has examples that were written in like 1990 and so on, and that still run. And although some of the styling of the text looks pretty ugly, and we're grappling with that right now, but that's a minor issue, so to speak. But it could be about anything. I mean, the thing you just mentioned, of course, the fact that works depends on the fact that in Wolfram language we have a knowledge base which knows about the battles in the Civil War, for example. So you're not going out and saying, oh, let me go find some data and clean it up and all that kind of thing. So another important thing about Wolfram language is the language is this precise symbolic language. But one way of inputting pieces of the language is using natural language. So, in a notebook, you type control equals, and then you might type battles in the Civil War. And then as soon as you hit enter, it will turn into the entity American Civil War, and then of the property battles. And so American Civil War is underneath its entity, quotes military conflict, comma, quotes American Civil War, and then battles underneath is the entity property military conflict battles. And if I evaluate that, press Shift Enter, I will get a big long list of entities like, the Battle of Westport, the Battle of Fort Stevens, and so on. Each of these is an entity of a military conflict entity. And each of these is like a symbolic expression. And each of those symbolic expressions I can do computations with. Like, for example, I can find out the geoposition of it or something like this. And but the whole point in a computational essay is that you're kind of sharing the load of creating the content, because you're writing the English text or the natural language text, you're writing the computational language input, but then the computer is automatically generating the output. So it's sort of, it might be a little bit more effort to get the computational language correct. You don't get to kind of just smoosh the words around like you would in natural language. You actually have to say something that's kind of precisely what you mean, so to speak. But the good news is that then the computer kind of generates the output. So you might have a very tiny piece of Wolfram language code, like this one that said American Civil War battles, and then you get this big long list of battles out, and then I could say geolist plot of that, and I would get what you might think a geoplot of where all those battles are. So that's kind of the idea. And it's sort of, as a programming language thing, it's quite interesting, this interplay between natural language and the programming language. What we found is that for things like specifying an entity or something, it's really, really useful to have natural language. You don't want to have a manual, a piece of documentation that lists all the military conflicts in history and says what their canonical names are. You just want to type, Civil War, and let's see if I do that here. I think it will default. Let's see what it does. So it says United States Civil War, but then it has a little ... here, which says alternate interpretations. So it says, assuming United States Civil War, use English Civil War instead. So you can click that to change the interpretation of that input. Or you can also, there are apparently some other things, a board game, a book, other kinds of things that are called the Civil War.
I want to back up because I think that you don't realize how different this is from how most programming languages work, perhaps. So you're saying that...
Oh, I do. That's why I don't call it a programming language.
Okay. So I kind of want to nail down this data thing because I think it's interesting. So I have a Wolfram Lang prompt, like it's like a REPL, and I can, type programs and ifs and such, but also I have just like data there.
Sure.
So I can do like Jupiter.mass, or I can do Civil War, or I was playing around with this actually. So there's like food in there, like lemon tart.calories. Like where does this data live? Why is it in the language?
Well, it's in the language because the purpose of the language is to express sort of everything in the world computationally. So this data is the knowledge base that we built over the last 30 years or so. We have been steadily accumulating, curating, making computable data about all sorts of kinds of things. So you'll find a couple of 100,000 foods. Foods are very complicated. They have a very complicated ontology, and lots of properties of different foods have different numbers of properties because people haven't necessarily measured the this content of the that. But most will have 20 or 30 standard kinds of nutritional pieces of data about them. But so yes, we have all the things that all sorts of data made computable, which is it's a high bar to make data computable. It's not good enough to just say, if you're dealing with, let's say you want to know about asteroids or something, and you want to compute, the largest 10 asteroids or something. It's not good enough to just say, well, we've got some asteroids. You've got to have sort of all the asteroids so that you can actually correctly compute the largest 10 asteroids. And it's taken a lot of effort to kind of accumulate all of this data about lots of kinds of things. And there's lots of real-time data, like all the real-time weather data or earthquake data or flight tracking data or whatever else.
So how does it work if you have real-time data? Like if I do like weather.now, will it tell me what it's like here?
This dot business is not really the right thing. If you say, say air temperature data, for example, the function is, for example, air temperature data of, and then pick a city. Where are you?
Peterborough, Ontario, Canada.
Okay, let's try Peterborough. Let's see what it does with Peterborough. Is it OROUGH or?
That's right.
Okay, Peterborough City. Okay, so it picked the one in Canada by default for me. So that's an entity. So for what it's worth, the Peterborough, the entity, if I say, what is that? What is the input for me? What I see on the screen is a yellow background box that has the word Peterborough and then the word city after it. But if I say, what's the input form of that? It will say entity, city, Peterborough, Ontario, Canada. Okay. Mm-hmm. So then I can say, let's say I say air temperature data. That's a function of Peterborough. Then I will get open bracket, I say air temperature data, open bracket, Peterborough. I will get, hopefully, some Result. Oh, it's loading in some. Okay, 34 degrees Fahrenheit, it says. So it's giving it in Fahrenheit because it knows I'm in the US. If I were to tell it, I could just say unit convert that to centigrade if I wanted to. Or I could go ahead and say air temperature data of Peterborough, comma, and then I could say like now minus 3 weeks.
So you have this entity, Peterborough, and you get the weather. Like that's making some sort of web service call somewhere that I don't know about. Like where does this all
No.
live?
Okay, so it's going. Yeah, I mean, yes, it is going to our cloud. So weather data is streaming in from the sources we use for weather data. We're storing all that stuff, and then this behind the scenes, the language is going out to our cloud to retrieve that data.
Okay. And what if I put in like mass of Stephen Wolfram? Like
I don't know whether. Let's see what happens. Let's see. I don't know whether that. Oh, Stephen Wolfram. Wait, let's see. Missing, not available. Sorry. Well, at least we understand what the question means.
There we go.
I could hook that up actually. Because we have this notion of data bins, which are again sort of symbolic objects that live in the cloud. And I have a data bin that a bunch of my personal analytics data is streaming into. And so, for example, if I went to that data bin, I could actually find out, how much I weighed this morning, so to speak. But that's not part of the public database. I'm not doing an Oprah like that. Maybe that's too long lost in history, that reference. I don't know. She was famous for having talked a lot about her weight on her television show.
You talked about Siri using Wolfram Alpha, and you have this knowledge base. Like, why not pure natural language?
You mean for everything? Well, okay,
Yeah.
so that's a good question. And here's the story. If you've got a sort of simple one-line question, how much does Oprah weigh? Right? Something like that. We can do very high quality natural language understanding on that. And we can sort of turn that into some symbolic form. We can compute the answer. We can give you back the result. Okay. But let's say you're trying to describe some more complicated thing. Let's say you're trying to define some algorithm and have it operate on images and do this and that and the other. Very quickly, natural language just completely falls apart. And fragments of it, like you say, I don't know, let's say you want the depth distribution of the Pacific Ocean, and you want that, only pieces that are this far away from Australia, and then you want you want the pieces that are within a certain distance of volcanoes, blah, blah, blah. Saying all of that in natural language is hard. Saying it in computational language, once you know the computational language, is very nice, very easy. And when you write it down in computational language, it's easy for other people to understand it as well. And, I found this really good sort of case of this. I wrote a book called Elementary Introduction to the Wolfram Language, which actually was sort of primarily aimed at kids, but has ended up being widely used by people other than kids, and as well as kids. But I decided to put exercises in this book. And the exercises basically have the form of write a piece of Wolfram language code that does X. And at the beginning of the book, it was really easy to do that, to write those exercises. But by the end of the book, it was super frustrating because, I immediately knew the code I want, here's how to express what I'm talking about in Wolfram language, in computational language. But, to be able to write that in English was actually pretty tough.
Would you say that your goals are that it is like a communication tool, or is the goal to be able to communicate to computers or to be able to communicate to each other using computers?
Both.
Both, yeah.
I mean, in the case of, look, 15 million lines of code inside Wolfram Alpha is, that's not intended to be read by a human.
Yeah.
But the things that you write in computational essays, absolutely, those are intended to be read by humans, but also executed by machine. So it's a language that scales very nicely from very small to very large, and the small pieces, the sort of human-sized pieces, are absolutely great ways of communicating. I would say that one of the things that I consider important about the language we built is that it is a language for thinking about things computationally in.
Mm-hmm.
So what does that mean? When I try and imagine how to specify something, I can immediately know, that, fold pair list is likely to be the functional programming construct that I want to use. And I can know that, I obviously used this language a long time, that is a way of organizing my thoughts about what I'm trying to do. If I didn't have that kind of primitive, I wouldn't organize my thoughts that way. I mean, I see this all the time because I see it particularly as we develop the language and as we finally condense a bunch of ideas into some new primitive in the language. I suddenly realize, all these things that I was thinking about in this kind of mushy way before, I can think about all of those kinds of things just using this, let's say, particular functional programming primitive.
It's a thinking tool. You're building some sort of augmented ability by using a computer to be able to reason about the world.
Yes, I see our computational language as something that helps organize human thoughts as well as defining to machines what we want them to do. I mean, in other words, if you look at sort of the arc of history on these kinds of things, a good analogy is mathematical notation. So back 400 years ago or something, when people were talking about math, they didn't have a notation. They didn't have plus signs and equal signs and so on. They just used words.
Mm-hmm.
And it was kind of clunky. And then people started inventing mathematical notation. And what happened fairly soon thereafter was algebra got invented. And then after that, calculus and so on. And basically, the sort of mathematically based sciences were made possible by the invention of this kind of notation that allowed people to organize their mathematical thoughts and communicate them. And in a sense, what we're trying to do, what I'm trying to do with Wolfram language is to provide a kind of notation for computational thinking. And, I think it's doing a good job at starting to enable a lot of these kind of computational X fields, just as kind of mathematical notation eventually enabled the kind of mathematical X fields. I think the big difference between our computational language and mathematical language, mathematical notation, is with math notation, you're still stuck with a poor human having to interpret the thing. The great thing about computational language is once you write it down, then a machine, AI, whatever you want to call it, computer, can take it away and do things with it. And that's really powerful. And I think that the way I see it, this is it's a form of communication.
The exploratory aspects are really where you're the most unique. It strikes me like I don't know of another computational essay tool. Have you tried, like bringing this to youth or people who aren't familiar with computer programming?
Because I talk about feeding this to kids, I actually feel like I have to do some field work. So I actually spend a couple of hours doing that with actual middle school kids and so on. It's a lovely contrast from what I normally do for a living of CEOing a technology company. But yes, absolutely, it's something where you can get to do computational X. You can get to really do sort of original, non-trivial computational things about the world, about topics you care about, and you don't have to learn how to write for loops and so on. I mean, it's kind of shocking in the little book that I wrote about Wolfram language. It has, I don't know, 50 chapters or something, and I think assigning values to variables doesn't show up until chapter 38.
Nice.
And I don't think loops, I don't believe loops ever show up. I mean, they obviously show up implicitly. It's there's the function table shows up very, very early, and map shows up pretty early, but I don't think, no, I'm pretty sure do does not occur in the book. And it's sort of interesting that I've explained what we call functions, which are basically lambdas, long before I had to explain assigning values to variables and so on. But so the main point is, with Wolfram language, one gets to actually sort of do things computationally without sort of going through learning kind of the low-level computer science, the traditional low-level programming language computer science stuff. I would say that in terms of kids, we've been doing for quite a few years a a high school summer camp.
Mm-hmm.
And it's always fun to go look on the web. You'll see the projects that the kids have done at the summer camp. And they're quite impressive usually. I don't know, we can go, let me pull it up and I can see what some of those were from last year.
So I pulled one up earlier. I think it was from this thing, but the one I found was it was this essay, I guess, but it was building a piano, and then at the end there was a little piano on the screen that you could like click on the notes and play it.
Yeah, I would say that's fun, but that's in the sense one of the more traditional kinds of you could imagine doing that in a bunch of other programming. Okay, I pulled up the ones for this year. So the first one was analyzing global emoji use, and I guess this was looking at Twitter and pulling out emoji and making a plot on a map of which countries have happy and sad emoji. The second one seemed to be tracking algorithm for squash. Okay, so I remember that one actually. That one was I didn't think that one was going to work, but it worked rather well. It was taking video images and finding the trajectories of squash balls in video images.
Oh wow!
It looked like another one here: automatic evaluation of relationships between characters and plays. So I suspect that was a combination of natural language processing. I see on the screen here a nice community graph plot.
These are high school kids?
These are high school kids, yeah.
This sounds like something that I wouldn't be able to do.
Well, but that's the point. That's the cool thing. It is a remarkable thing that what gets taught in, kind of, I don't know, when you get taught about computation and you think, well, I'm getting taught computer science, I'm learning how to do for loops and so on. But that's not really what's involved in doing sort of computational thinking for a real purpose. I mean, I think that I'm sure in one of these, I don't know, like the example here of evaluating relationships between characters and plays. I'm sure what actually came up there, I can click on and find out what happened there. But I'm sure what actually came up was all sorts of things about how do you find, given the text of a play, how do you actually pick out, what were the what was the description of, this is a character, how do you find the boundaries of the scenes and so on. And each one of these things, there's probably some idea that you can have. Oh, well, if there's a, paragraph break between this and this, that probably represents that. Okay, so the trick is, can you easily go from that idea to an actual piece of computational language code that implements it? And the whole point is to have primitives that are high enough level that the things you think in terms of are the primitives that are provided in the language. You're not having to think, how do I break down that thought into, sort of linked lists and array references and this and that and the other. You're rather thinking, oh, I want to break up the text into sentences. Okay, there's a function called text sentences that does that, etc. And in terms of language design, the big sort of challenge, I suppose, is, there are now 6,000 built-in functions in Wolfram language. And kind of my big job over the last 3 decades has been sort of keeping the design of these things coherent and consistent so that, once you know about how things work with text or something, you are immediately helped in understanding how things are going to work with images or graphs or whatever else. And I think one of the processes actually that's been kind of fun. So, I've been doing language design and design reviews for decades now. Mm-hmm. And the last year and a half, I've started doing something kind of fun with these, which is, pretty much every day I'll be doing some design reviews for working out various kinds of language design. And I started about a year and a half ago live streaming a bunch of these things. And so now I think I just did my 300th episode of live streamed design reviews.
Yeah, this is kind of wild. So I watched one of these. So you are just on Twitch, just like meeting with people and trying to like live coding, like you've been doing a little bit here, and playing around with the language and making decisions. What does the live element add to it?
I wasn't sure. I thought what we're doing is kind of interesting. It might be fun for people. Why not put it out there and see what happens? It turns out we've started to get lots of sophisticated users of our products and experts in all kinds of things who, log in and they make real suggestions, and they're pretty useful. And that's it's a pretty nice dynamic. And they'll send little code fragments and so on, and send references to papers to look at and things like that. That's one unexpected feature. Another thing is actually the archives of these things are pretty useful for us internally. I think they're also useful for people who are using our language and want to learn how to do design of things in our language. So, for example, we recently started this thing we call our function repository. And it's a question of, that function repository is supposed to follow our design principles. Well, if you want to understand the thought processes that go into our design principles, then these live streams are a good sort of source of that, of understanding that. I think, it's also, it kind of is, when people say, oh, I want to come work at your company, what's it like? Okay, you can, there's whatever it is, 600 hours of live stream meetings. You can find out what it's like. You like it, you don't like it, whatever. We've done a few live streams with some outside experts, and we'll probably do more of those. That's kind of an interesting dynamic. We have plenty of in-house experts on plenty of things, but sometimes we're trying to learn about stuff that we don't have a lot of internal expertise about. But I think, the main dynamic about design reviews is more sort of the underlying process, which is, it's all about sort of drilling down. What is language design really about? It's really about sort of imagining all the different kinds of programs, all the different kinds of things people might want to represent in one's language, and trying to kind of drill things down to some essential features that allow one to sort of define the right primitives from which all that stuff will be built up. And in a sense, for me, I've worked on a bunch of different kinds of things in my life in science and technology and so on. But for me, I think language design is the most pure kind of pure focused intellectual activity that I know, because it's all about what is the essence of what's going on in something and how do you represent that. And it's often hard work. If you get it right, honestly, people don't even notice. It's the little places that are brayed because you got it wrong that people will notice and say, oh, it doesn't seem to work quite right type thing. If you get it right, it's just like, oh, of course that's how it works. And people sort of don't really notice the language design if the language design is good. They only notice implicitly by the fact that they can be very productive in what they're doing. And it's pretty neat, actually, watching people, I don't know, particularly the younger crowd who seem to be often very, very fast at writing things in Wolfram language. We actually have a live coding competition that we do at our annual technology conference and a few other places. We just did one of those, and I didn't compete in it. I decided I shouldn't do that because I think I wouldn't win. And one of my kids actually is also, I think, has to be disqualified because he's too quick at writing Wolfram language code. But I think it is quite impressive and interesting to see how quickly quite non-trivial kinds of computational things can be done by people who know the language well. That's very satisfying to a language designer. So, for example, one could even imagine, if the language is well designed, then the typical thing you want to write will be a nice succinct piece of code. And if there's this weird, blob off the end of the code, that's probably a bug.
Yeah, that makes sense. But there's varying use cases, I guess. Like I'm thinking of, okay, Jupiter. Should that be Jupiter the god, or should it be Jupiter the planet, or?
Right. Well, so let's see what happens if we type that in. So if I say control equals Jupiter, okay, so it defaults to the planet. It has a little ... here. It says, assuming Jupiter is a planet, use as a mythological figure or a given name or referring to a fictional character instead. So at the stage of input, if you give natural language input, at the stage of input, it will do that disambiguation. Once you've pressed, there's a check mark next to the little yellow box here. Once you press that check mark, you will then get a definite. So let's say I pick mythological figure instead. Okay, the way it works is it's called the ambiguity function as part of these things called interpreters, which are part of the language, which are the way that that's the symbolic representation of the process of interpretation. But in any case, it's always working the same way of if you're using natural language and there's like for example in the stuff I was doing on my physics project, I suspect I was writing Wolfram language code for hours without touching anything in natural language. There was no reason to, because it's
precise, or
it's because I'm thinking about it in Wolfram language, basically, and I'm not trying to relate it to things that I better can express in natural language. Now maybe if I was sort of if I never used the language before, there might be things that I would like to type in natural language, because that way I can just use natural language and not have to go, and maybe it saves me from trying to understand the computational language myself at first. But I think very quickly, I mean, that kind of another sort of idea of language design is, Wolfram language is a very big language. It's something. There's no other, no programming language is this big. Nothing like this big. I mean, they might have a few tens of keywords. We have 6,000, in many cases, very complicated, highly sort of functions, with many of them are kind of super functions that, like there might be one called classify, or there is one called classify that just uses machine learning to classify things. So that's a sort of a big super function, so to speak. So there are 6,000 of these things. And the question is, how can one deal with something that big? And the answer is by making everything very consistent. So people have to learn only a small set of principles, and then are kind of off and running with sort of low cognitive load. They can kind of deal with other parts of the system once they know those principles. Now, it's a huge amount of work to maintain those principles. And here's what I realized. You look at these libraries, I don't know, there might be Python libraries, or they might be Java libraries, or whatever else. And there'll be a few really core functions that are really the things people care about in those libraries. But then there'll be a lot of stuff that has to support those things. Let's say it's a thing where you're doing some particular operation on images. Well, there's all kinds of things in that library for reading in images and writing out images and converting formats of images and this, that, and the other. And what typically happens is that, or maybe you include some other library that does a bunch of those things and so on, you've got a lot of work to do to sort of deal with the infrastructure of what's going on before you get to your master function, so to speak, your top function. And what I realized in the function repository that we built, I wasn't sure what was going to happen with it, and it's actually working really great, that people can add just these single functions that do very powerful things, and they can just add that one function because all of the support stuff is already in the language. They don't have to say, how am I going to represent the image? Well, there is there's just a way to represent images. They don't have to sort of rebuild the infrastructure every time they want to get to a piece of functionality. So that makes it possible. And it also helps a lot having a symbolic language where you can kind of have different kinds of things that are manipulated in a very uniform way, because everything is a symbolic expression. An image is a symbolic expression, a user interface is a symbolic expression, a cloud object is a symbolic expression.
If I ask you about the language and you're like, yeah, it's batteries included, it has everything, and I could be like, oh, you mean like image processing? And you're like, well, image processing, but also Oprah Winfrey. And
yeah, right. What we've done, for better or worse, it's a very unique thing. And I have only, this idea of trying to make a really integrated sort of full-scale computational language, it just hasn't been the ambition or the activity, basically, anybody else. And I've been, I'm not sure I would, since I've spent a large fraction of my life doing this, I can say it's been hard work. I mean, you have to kind of keep at it sort of every day for decades to do this. And I think it probably matters that, I've personally kept at it, and it's had sort of consistent leadership over a long period of time. I think that, there's sort of a strange set of circumstances that have made that possible. And in a sense, what the thing that we've bitten off to do is a big thing.
It strikes me that like you have just built like what you wanted. You've built this whole company and language around this idea of building this tool that's how you want to like think about the world or the questions you want to ask of the world. Is that at all right?
Yeah, that's true. I built something that I wanted to use, and I built something that for me has proved to be a wonderful kind of mechanism for helping me kind of define my thoughts about things. And I'm glad to see it's useful to other people too. I think that it's something where it's kind of when we think about what's possible with computation and what's possible with AI and so on, there's this big issue of sort of there's an ocean of possibilities with computation. And actually, I happen to have spent a bunch of time studying sort of the basic science of that, of sort of what can happen in the computational universe of all possible programs and so on. And there are lots of really amazing, elaborate things that can happen, some of which the natural world happens to use, much of which the natural world doesn't use, much of which we've never used in our technology and so on. And the question really is, given this sort of ocean of possibilities that computation provides, how do we define which ones we care about, what we actually want to do? And I kind of see computational language as being the way that we make a bridge between what is sort of theoretically possible with computation and the things that we humans happen to care about. I mean, in a sense, the things we happen to care about represent this sort of slice defined by our civilizational history relative to what is conceivable, so to speak. I mean, there's and in a sense, sort of the language design is that bridge between what is computationally conceivable and what it is, and the ways that we humans like to think about things and the kinds of things we choose to think about, so to speak.
That makes sense. Like the temperature in Peterborough, I guess it's somewhat arbitrary, but it's something that is useful for us as humans because
Exactly. I mean, the very concept of Peterborough is something that is a human construct. I mean, we could say the geolocation on the Earth, or we could say, all kinds of things. I mean, the fact that we're choosing that as opposed to, temperature is we could ask for something about the dispersion of the velocities of the gas molecules in which wouldn't be, whereas the temperature is, kind of the average velocity of the gas molecules. We could ask for something different than that, and just doesn't happen to be something we care very much about. The thing that you realize, so I've spent a bunch of time sort of studying the basic science of extremely simple programs and what they do, and kind of the remarkable thing is that even programs that you can define in sort of half a line of Wolfram language code, or you can just say, you got a row of black and white cells, and based on the color of each cell and the color of neighboring cells, do this on the next step type thing with a little table. Just with programs that simple, it's really easy to find examples where the programs do really complicated things that one would never expect from just looking at the program. Now, some of those programs will make, I don't know, nice nested patterns. Some of them do things that we can immediately say, oh, that would be useful for image processing or something. But many of them just do what they do. And it's just like, okay, that's nice. But we humans don't have any particular reason to care about it. I mean, sometimes people use them to make artistic works or something like this, where kind of the thing that's important about it from the point of view of us humans is that we find it aesthetic or something like this. There's this, as I say, there's this huge realm of possible computation out there, and the question is, which parts of it do we care about? I mean, I've spent a bunch of time sort of studying kind of the total universe of simple programs. In the case of neural nets and deep learning and so on, we're dealing with more complicated programs, but and ones where we're kind of incrementally exploring by sort of an evolutionary type technique, or a kind of a gradual adaptation type technique. We're kind of exploring the space of possible programs. And again, we ask the question, of all the conceivable arrangements of weights in a neural network or something, which are the ones we care about? Which are the ones that do something that is of relevance to us? We train an image identifier. We're training it on things that actually occur in our world. We could as well train an image identifier on something that is completely bizarrely, these bizarre abstract shapes or patterns or whatever. But then we don't have that doesn't connect with things we care about. And for example, in the case of an image identifier, we wouldn't have defined concepts that represent those things that we just sort of made up. We've defined concepts for things that our civilization has found useful. We've got a concept for a chair or a table or something like this. And what's sort of interesting to me in the evolution of these things, if you look at human language, it evolves based on the things that show up in the world. Like a word like podcast didn't exist before those things kind of showed up in the world. And now when we say podcast, that comes with a whole bundle of kind of conceptual sort of things we think about. But the fact that that word was worth inventing was a consequence of something that existed in the world. But once we've invented that word, then we can sort of reason in terms of it and build things on top of it. And that's very much the same process as what goes on in designing computational language, that, once you've invented subset map or something, then you think of lots of kinds of, I don't know, functional programming operations or whatever it is in terms of that concept that one has now invented. So it's sort of a funny loop that goes between the what gets described in a language and what people choose to build, and then what people choose to build being what ends up defining what's worth defining in a language.
So an interesting example of this computational essay, to bring it back, is like your book, right? So your book, I feel like I have to plug it since your publicist set this
Good.
up. But so, like I'm looking at an essay here called The Data Science of Facebook. And it's sort of, I think it's a good example of what you're talking about earlier. Like it's prose, then mixed with like calculations and graphics.
Right. And I mean, the version of that there's this one, there's probably an online version of this that actually has the code. Oh, that one, unfortunately, the code is there. The data we cannot expose for that particular one. But I mean, the raw data. This was a thing we did back in 2012 or so. Facebook used to have this very rich API that they exposed, and we provided something in Wolfram Alpha where you could go and kind of find out what Facebook knew about you, and it kind of generated this, I don't know what it was, 30, 40 page book effectively of kind of, where your friends live, what the popular words on their feeds were, and all sorts of things. I don't remember all the details, but for a while we were just like, people would connect to the Wolfram Alpha. We could connect Wolfram Alpha to their Facebook accounts, and it would generate all this stuff, and then we'd throw the data away in an hour. This essay was the result of doing some analysis of things like, what is the distribution of ages of people's friends relative to their own age? And you kind of see it's very tightly peaked, but until people get to about age 35, and then there starts to be a little an earlier peak, which gets bigger, which is people friending at least back in those days, people friending their kids and their kids' friends and things like this.
It's super interesting as an example of kind of the thing you're talking about. So I recommend people check out that book. So this has been great.
This was good. We got to talk about lots of nice computational language stuff, which I always like talking about, and hopefully your listeners will find of interest. I mean, I think, one of the challenges in what we're doing is that it's different from what's been done, what's done elsewhere. And so it's funny, I if I look at things I've done in my life, there are quite a few things where I figured out something that I thought was important, like the use of programs instead of equations to model natural systems and so on, a bunch of other kinds of things. And then people said, oh, no, that can't possibly work. Oh, no, we don't understand it, et cetera, et cetera, et cetera. And then, a couple of decades goes by, and yep, that's how people think about things now. And it's kind of interesting to see this inexorable thing that happens because, I think my sort of self-assessment of my ability to figure out what's going to happen is that I'm pretty good. I don't necessarily get the time scale right, but I'm pretty good at figuring out what's going to happen. And I think with this whole computational language thing, it's absolutely inevitable. I mean, this way of setting things up is what people are going to become used to, and there's going to be sort of a level of computational language literacy that starts to develop, and that's going to be the future. It may be a while, but it's kind of amazing how much one has to kind of sort of explain it over and over again. And it's funny how the world works because, you can explain these things a bunch of times and people don't get it. And then, a decade goes by and sort of it slowly seeps into kind of general consciousness. And then eventually people think it's obvious. right? And so, this will be obvious one day, but it isn't yet. I mean, it's like notebooks, for example, which I always thought were completely obvious, back when we invented them. And then people were saying, oh, no, this is, how can we possibly understand this as an interface to a computer system? And then, in that case, nearly 3 decades went by, and it's like, oh, yeah, of course, this is the obvious way to do it.
Well, thank you so much for your time, Stephen. This is Adam Gordon Bell from Software Engineering Radio. Thank you, everyone, for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.